Okay. Hello everyone. So in this lecture, the next video of this lecture, we're going to talk a little bit further about what we should care about, should look for or be concerned with when estimating these models, right? So the concept I want you to bring your attention to is the concept of spurious regression. Spurious regression refers to uh, uh, a regression estimation where um, you observe a relationship when there actually isn't one, right? So here's the thing, estimating the impact of X on Y with time series data can be tricky, right? Due to the nature of the data that tends to show an effect, even when one does not exist. Okay, so we refer to this situation that there is a risk of estimating a spurious regression. Spurious regression. Okay, spurious regression refers to a regression estimate that shows a significant relationship between two unrelated time series. Right? Of course, we're looking at time series data that all the variables are time series. So even though they're not related, it shows that there is a relationship, and that could cause us to uh, misinterpret the situation. Okay, why does it occur? What? Okay, sorry about that. The most common reason is that the time series used are not stationary within the range being estimated. Okay, let's take a look. All right, an example. This is a common worldwide example used. Ice cream sales and shark attacks. If you look at the data on ice cream sales and shark attacks, daily during these few months, what you're going to see is that starting from May, right, the time series of ice cream sold is going up. At the same time, shark attacks are going up, right? So in this situation, we would statistically note that there's a statistical relationship between ice cream sold and shark attacks, right? Yet, it is clear to most people that ice cream sales do not cause shark attacks, right? The two are unrelated, right? However, here's the tricky thing. If we estimate the regression just like this, we will get a significant estimate, right? Imagine taking these dots, and plotting scatter plots of ice cream sold and shark attacks and estimate a linear regression line. You're going to get a positive effect, right? This is because during this period, both variables are experiencing a trend, in this case, upward trend. Okay? Time series that have a trend, among others, are said to be non-stationary. All right, so that's the key. Spurious regression tend to be caused by non-stationarity. So what we have to look at next is what is stationarity? Okay, a stationary process. Now, the word here is a technical term, so you're gonna have to, note that stationary, right? It's a technical term. A stationary process or time series has constant mean variance and autocovariance. Autocovariance just means the correlation across time period for the same variable. Okay. Over time. So a stationary process has a constant mean variance and autocovariance structure, no matter what time period you look at. So the state of being stationary is known as stationarity. Stationarity. I know it's a mouthful, but you're gonna have to get used to it because you're gonna have to say it a lot. Stationarity. Non-stationarity consequences lead to spurious results in regression, observing a relationship when there actually isn't one, and which means that your predictions, which you use the model to predict, as well as statistical inferences, the significance, all that stuff, is not going to be uh, valid in the sense that you expect, right? The relationship does not really exist, but the evidence shows that it exists, right? Predictions are going to tell you that if X goes up, you expect Y to go up. If ice cream sales go up, you expect shark attacks to go up. But it may not work all the time because in some other cases, maybe the trend goes down instead, and you're going to observe different things, right? So we need your time series data to be stationary in order to estimate models where you have X predicting Y. Okay, so that's very important. So based on that, how do we tell if our data is stationary? Right? There'll be a statistical test, but first you can take a look at the time series plot itself. For a stationary time series, you'll notice for the top one, right? Stationary time series tend to have some kind of a central value where it tends to come back, right? For in this case, it jumps up and it goes way down, it goes up again, down again, but it kind of does that around a central line. In this case, seems to be around zero here, right? In some short period, there seems to be kind of a keep going up and all that, but it comes back down, right? So stationary time series will look, it all also depends on the range of time that you're looking at, right? A time series could be stationary in the long run, but non-stationary in the short, sorry, could be stationary in the short run, but non-stationary in the long run, depending on how short or how long you look at. So if you look at in comparison, non-stationary time series, it tends to, if it goes down, it's going to keep going down for a while. If it goes up, it's going to go up for a while. In other words, the graph is going to be smoother. That's the thing. That's the kind of something seems to be unexpected. If the graph is smoother, it's non-stationary. And so it's going to have some kind of persistence. It tends to stay where it is or go up if it went up before, it's going to keep going up, right? So stationary data would show tendency for mean reversion, reverting back to the mean, reverting back to its central value, right? Going back to the mean value after some time. While non-stationary data tend to show persistence, meaning that if it goes down, it's going to keep going down. If it goes up, it's going to keep going up, right? Over time, it's going to keep going down or going up. In this case here, not only do we see that it has some kind of a trend, it also tends to become more volatile over time as well, as the variance is not constant too. Okay? Visually, that's what it looks like. Now, what we can do is we test for it statistically. In particular, we test for this situation called unit root. Okay, use the Dickey-Fuller unit root test. I'll talk about what unit root means later on. But for now, it's enough to just know that we test for it statistically, right? Based on this test. If the time series is unit root, does not revert to a mean. Unit root means if it it's going to keep going up if it was going up before and so on. It keeps adding to the old value. It doesn't go back. That means it's non-stationary. So the unit root is the most common, typical way that time series is non-stationary, especially for economics data. Economics data. Okay. So we just test for unit root. We estimate the equation on the left here and test for delta equal to 0. Yeah. We have the null hypothesis of 0, alternative hypothesis not equal to 0. If you reject the null hypothesis, then your time series is stationary. Right? So the null hypothesis is non-stationary. Right? Dickey-Fuller test. There's some technical issues to talk about here quickly. The statistical test for Dickey-Fuller it doesn't use the normal distribution for test statistics. It's a Dickey-Fuller distribution. They derived the distribution and came up with the significant with the critical values and so on. So even though the distribution is not normal, it's Dickey-Fuller distribution, but the concept of the test is the same. Reject HO, we have stationary. If we do not reject HO, you have non-stationary. All right, let's look at an example here for NVIDIA monthly stock price. In this case, for non-stationary testing for stationarity, you look at the NVIDIA price that I downloaded. It looks like this. It was going up, down, and up again. Doesn't look stationary, so I think visually we can see it's not stationary. But we do the Dickey-Fuller test in Stata. The command is dfuller followed by the variable. Okay. Now, because there's a lag value in the equation to estimate, here there's a lag value, the number of observations becomes smaller, 59. Okay, doesn't matter. Here's what we look at. We run the test, we look for the p-value. P-value, you compare that with the significance level. Conventionally, we're looking at 10%, 5%, or 1%, right? In this case, the p-value here is actually 80.9. So if we conclude non-stationarity, if we conclude stationarity, if we reject the null, the chance of being wrong is 80%. That's not a good chance, right? So in this case, we do not reject the null hypothesis of non-stationarity, right? So the test shows non-stationarity. P-value is not significant. Okay, so I'm just gonna go ahead and stop this video here, and you guys can try to run the Dickey-Fuller command on your the stock of your choice. Okay, so yeah, we'll just pause this video here.